In this video, we're going to go over the LR circuit. So let's work on this problem. A 12-volt battery is in series with a 10 ohm resistor, an open switch, and a 200 millihenry inductor. So let's draw a circuit. So here's the battery, and then here is the open switch with the resistor and the inductor. Now what we have is a 12-volt battery, and this is a 10 ohm resistor and a 200 millihenry inductor. What is the current flowing in the circuit after the switch has been closed for a long time? So at t is equal to infinity, the current is going to be at a maximum once we close the switch. And so that maximum current is simply the voltage of the battery divided by the resistance of the circuit. So it's going to be 12 volts divided by 10 ohms, which is 1.2 amps. So the maximum current, which I'm going to call I0, that's 1.2 amps. And so that's the answer for part A. Part B, what is the value of the time constant? The time constant is represented by the symbol tau. And to calculate it, it's equal to the inductance divided by the resistance. So the inductance is 200 millihenries, or 200 times 10 to the minus 3 henries. And the resistance is simply 10. So the time constant is 0.02 seconds, which I'm just going to rewrite this here. And so that's it for part B. Now, part C. How much current will be flowing in the circuit after 10 milliseconds? So after a time period of 10 milliseconds, what is the current? Now, 1 second is 1,000 milliseconds. So to convert 10 milliseconds to seconds, divided by 1,000. So 10 divided by 1,000 is 0.01 seconds. So now, how can we use this information to calculate the current? When the switch is closed, the current is going to increase from 0 to 1.2. And so we're going to have a graph that looks like this. So this is the current on the y-axis. On the x-axis is the time. And this is the maximum current. So that's 1.2 amps. And so it's going to start from 0 and gradually increase to its maximum value. And so that graph is represented by this formula. So the current is going to be the maximum current times 1 minus e raised to the negative t divided by tau. So in this example, the maximum current is 1.2 amps. The time is 0.01 seconds. And the time constant is 0.02 seconds. So go ahead and type that in exactly the way you see it. So the current at 0.01 seconds is going to be 0.472 amps. Now there's another equation that you need to know when dealing with inductors. You don't need it for this problem, but this is just some extra information. Let's say if the switch is closed and then you open the switch. You need to know what happens when the inductor releases the energy that's stored in a magnetic field. So when it releases its energy, the current is going to start from its maximum value, and it's going to decrease like this. And the equation that corresponds to that graph is this equation. So you need this equation if the current is decreasing. If the energy is being released by the inductor to the circuit, and for the other equation, let's say if energy is going into the inductor, if the current is increasing, that is this situation, it's going to be I is equal to I0, 1 minus E negative T over tau. So the difference is the 1. That's when the current is increasing. But if it's decreasing, just that 1 is not going to be there. So those are some equations that you want to use for this type of a problem. Now let's move on to part D. What is the voltage across the resistor and the inductor at t equals 10 milliseconds? So at 10 milliseconds, we have this current. So the voltage across the resistor, it's just going to be the current that flows through the resistor times the resistance. So the current at this instant is 0.472 amps. And the resistance is 10 ohms. So then that's going to be a voltage of 4.72 volts. Now, to calculate the voltage across the inductor, we need to realize that the voltage drops must be equal to the voltage of the battery. So it's going to be 12 minus 4.72. So the voltage across the inductor is 7.28 volts. Now, it's important to understand that this voltage is positive because that battery delivers energy to the circuit. And these, they're negative because as the current increases, they consume energy from the circuit. So they cause a voltage drop. So VL is negative 7.28 volts, technically speaking. Now part E, at what rate is the current changing at this instant? So the EMF across the inductor is equal to the inductance, it's negative L, times the change in current divided by the change in time. In some textbooks, you'll see it as di over dt. And for the most part, di over dt is approximately the same as delta I over delta t. It's the change in current per change in time. Now the EMF induced by the inductor is this value. So that's negative 7.28. And that's equal to negative L, which is 200 times 10 to the minus 3 times di dt. So negative 7.28 divided by negative 200 times 10 to the minus 3. That's equal to this number, but let me make some space first. It's positive 36.4 amps per second. So that's the rate at which the current is increasing per second. Now we know it should be positive because we're dealing with this situation. When the switch closes, the current is going to increase from 0 to 1.2. So therefore, if the current is increasing, di dt should be positive, which means the voltage across the inductor has to be negative, which fits well with this equation. So it's important to understand that as the current in a circuit increases, the inductor, it stores energy. So it's absorbing energy from the circuit. And that energy is used to build up the magnetic field that's inside the inductor. So the EMF generated by the inductor is negative. That's the induced EMF. If the current is decreasing, the induced EMF will be positive. So you're going to have a collapse in magnetic field, and the energy that's stored in that magnetic field is being transferred back to the circuit. So if you increase the current in the circuit, the inductor is going to try to oppose that increase in current, and it's going to absorb energy, causing the current to increase slowly rather than rapidly. Now, if the current decreases, the inductor is going to use its stored energy, and it's going to release it into the circuit in order to maintain the current. And as you can see, when the current decreases, the EMF is positive. The inductor is trying to support the decrease in current. So those are some things to know. So if the current is increasing, the voltage across the inductor is a voltage drop, just like the resistor. The resistor absorbs energy from the circuit. But if the current is decreasing, the inductor will be basically, what's the word I'm looking for? It's going to act like a battery. It's like a voltage boost or a voltage lift. It's going to increase the energy of the circuit if the current's decreasing. Now let's move on to the last part of this problem. How many time constants will it take for the current to reach 99.4% of its maximum value? So keep in mind, tau is 0.02 seconds. So first let's start with this equation. So the current is equal to the maximum current times 1 minus e raised to the negative t divided by tau. So let's rearrange the equation and solve for t. So first, let's divide both sides by I0, the maximum current. So we have I divided by I0, and that's equal to 1 minus e raised to the negative t over tau. So what I'm going to do now is I'm going to take this term, move it to this side where it's going to be positive e. And then I'm going to take this term, move it to that side where it's going to be negative. So I'm going to have 1 minus I over I0. So now I'm going to take the natural log of both sides. A property of logs allows you to take the exponent and move it to the front. So now what I have is negative t divided by tau times the natural log of e. And so that's equal to ln1 minus I over I0. So at this point, we can get rid of ln e. Ln e is equal to 1. So we have negative t divided by tau. That's equal to ln1 minus I over I0. So now I'm going to multiply both sides by tau. And so these will cancel. I'm going to multiply both sides by negative t. So I can get rid of the negative sign as well. So t is equal to tau, that is negative tau, times the natural log of 1 minus I over I0. So now let's finish it. So I want to get the number of time constants. So I want to get t in terms of tau. So I'm not going to replace tau with 0.02 seconds right now. Now we want the current to reach 99.4% of its maximum value. The maximum value is 100%. So I'm just going to replace I0 with 100. And then I'm going to replace this with 99.4%, which is what we want to reach. So 99.4 divided by 100 is 0.994. So ln1 minus 0.994, that's equal to negative 5.116. So the two negative signs will cancel. And so it's going to take about 5.116 time constants for the current to reach 99.4% of its maximum value. So this is the answer. Now, if you need to get the time in seconds, simply replace tau with 0.02 seconds. So 5.116 times 0.02. So that's about 0.102 seconds. So that's how long it's going to take in seconds for the current to reach 99.4% of its maximum value. Number 2. A battery is in series with a 25 ohm resistor, an open switch, and a 350 millihenry inductor. The current in the circuit is 174 milliamps after the switch has been closed for 8 milliseconds, and the current is increasing by 16.1 amps per second at that instant. What is the voltage across the resistor? So let's draw a circuit. So initially the switch is open, we have a resistor, and we have an inductor in series with the resistor. So let's call this VB. We don't know the voltage of the battery. The resistor is 25 ohms, and the inductor is 350 millihenries. Now, to calculate the voltage across the resistor, it's simply going to be the current that flows through it times the resistance. So the current is 174 milliamps, which is 0.174 amps. And the resistance is 25 ohms. And so that's equal to 4.35 volts. Part B. What is the voltage across the inductor? So let's calculate VL. It's equal to negative L times di dt. So in this example, L is 350 millihenries, or 350 times 10 to the minus 3 henries. And di dt, that's the rate at which the current is changing. So it's increasing, so it's positive. It's increasing by 16.1 amps per second. And so this is going to be negative 5.635 volts. The negative sign tells us that the inductor is consuming energy from the circuit. So it's storing up energy. It's decreasing the energy of the circuit. And the resistor does the same thing, so the resistor always consumes energy from the circuit. The battery is going to increase the energy of the circuit. It's delivering power to the circuit. So if we were to write an equation that will help us to calculate the voltage of the battery using Kirchhoff's voltage law, as we travel in this direction, this is going to be positive, negative, positive, negative, positive, negative. So as we travel through the battery, we have a voltage lift. The current is going to flow in this direction. Now the current flows from positive to negative, so we're going from high potential to low potential. So that's the voltage drop. And here it's going from high potential to low potential, so that's another voltage drop. VR is going to be IR. VL is L di dt. So this quantity is already negative. That's negative 4.35. We don't have to use the negative twice. And this whole thing should be negative as well, since it's decreasing the energy of the circuit. So that's going to be negative 5.635. So if we take these two and move it to the other side, we can see that VB is 4.35 plus 5.635. So the voltage of the battery is 9.985 volts. So I'm going to rewrite these values on top. So VB is 9.985. VR is negative 4.35. And VL, negative 5.635. And so that's it for part C. Part D. At what rate is energy being delivered by the battery? So basically, we need to calculate the power delivered by the battery to the circuit. So we could use the voltage of the battery times the current. So the voltage is 9.985, and at this instant, that's when t is 8 milliseconds, the current is 0.174 amps, or 174 milliamps. So this is 1.737 watts. Now, because the battery is delivering energy to the circuit, I'm going to define the system as the circuit. So the system is gaining energy, so we're going to assign this a positive value. Now the resistor consumes energy, so I'm going to assign a negative value for that. And so it's equal to I squared R. That's the power absorbed by the resistor. So the current is 0.174 amps. We need to square that, and the resistance is 25 ohms. Now I'm going to assign a negative value to this, since the resistor consumes energy. So it's going to be negative 0.7569 watts. And the inductor, when the current is increasing, the inductor will consume energy. It's going to have a negative EMF value. But if the current is decreasing, the inductor will increase the energy of the circuit. So you need to be careful when dealing with the inductor. So for the inductor, it's going to be the voltage times the current, and the voltage of the inductor is negative L di dt, and then times the current. So it's going to be negative L is 0.35 henries, di dt, that's 16.1, and then the current is 0.174. So negative 0.35 times 16.1 times 0.174. So this is going to be negative 0.98 watts. So if we add up these two values, that's going to give us negative 1.737. So notice that the energy delivered by the battery to the circuit is equal to the energy consumed by the resistor and the inductor. So therefore, the rate at which energy goes into the circuit is equal to the rate at which energy leaves the circuit. The rate at which the battery puts energy into the circuit is equal to the rate at which the resistor and the inductor consumes energy from the circuit. And so you have conservation of energy in this example, which should always be the case. So that's it for this video. Thanks for watching, and have a good day.